All right, chemists, let's get started. It's exam week. You guys, this is my 11 a.m. class. Your exam for the majority of you is on Wednesday evening. It's not tonight. That's correct, right? It's on Wednesday evening because we couldn't get the exam room on Tuesday. So do not show up to the exam room on Tuesday. You'll probably walk into a statistics exam. So our exam is on Wednesday. If you talk to your other friends in Gen Chem, they might have it on other days. That's okay. Just follow the syllabus. I will be there tomorrow evening. So plan is for today. I want to start a little bit of chapter 7. We're not going to spend any more than 30 minutes on this, and then the rest of the class we will do midterm 2 review. And so there's a reason I kind of want to push ahead. If we push ahead enough a little bit, I may be able to cancel a class, such as the week of Thanksgiving. How does that sound? Yeah, we'd like that? Okay, all right, so let's do chapter 7 then. Okay, all right, so in chapter 6, we learned about electrons, the real way we consider electrons. So what was the most recent theory of electrons around our atoms that we learned about in chapter 6? Was it Rutherford's model? Was it the Bohr model? What model is the current model? The Schrodinger equation. Do we ever have you guys solve the Schrodinger equation? No. And so what the Schrodinger equation tells us is all of those quantum numbers. All right. The Bohr model did not talk about quantum numbers. It only alluded to the n energy level quantum number, but none of the other ones like M, L, L, and electron spin. So the Schrodinger model is our most current model that we consider today. So now that we know more about electrons, let's see how electrons behave and relate to the behaviors that we see of our elements and compounds. So a lot of the memorization I made you do in chapter 2, like memorizing the charges on the periodic table, the reason sodium always forms a +2 cation in an ionic compound is due to energetics. So it comes back to thermochemistry. So now that we know more about the electron, let's look and see, okay, how do those energies relate to those behaviors that we see, such as the ionic, typical ionic charges. All right, and so this will explain via energy those properties that we see. All right, so we're in chapter 7, so that means we're halfway done with Chem 1210. Isn't that gross? That's gross. Yes, yeah, we're halfway done through the semester. Okay, so we'll talk about how the periodic table was developed, our modern day periodic table, and today we'll just talk about effective nuclear charge. This concept explains a lot of the behaviors that we see. So effective nuclear charge might be a new topic that you might not have seen before, but it helps us predict behaviors that we see of electrons. And then it relates to a lot of the properties that we see in trends such as size, ionization energy, and stuff like that. It all comes back down to effective nuclear charge. Okay, so we know what our periodic table looks like now. It looks like this weird castle. All right, so historically it took a lot of different scientists to come up with our modern day periodic table, but we need to put ourselves in their shoes a bit. They actually discovered this periodic table, like the actual current shape of it, before they discovered electrons. So to us, it's really easy to think, oh yeah, just put the elements in order of their atomic numbers, or in order of the number of protons that they had. But the problem is that these scientists, they didn't know what protons were. Right? So it's kind of like a guess in the dark, the order of our periodic table. So they had to be clever in order to put in order the periodic table to the shape and the order that it is today. So historically, there were 2 different scientists involved with our modern day periodic table, Mendeleev and Meyer. But the problem is that we don't typically talk about Meyer. So both of these scientists, they basically discovered the periodic table at the same time. But we, as modern day chemists, we just remember Mendeleev and his work. And there's a reason he's more remembered than Meyer. And the reason is he realized, he ordered the periodic table based upon repeating properties that he saw. So he saw that lithium, sodium, potassium, those elements have similar properties. So he put those on top of one another in a group. And that's how we understand, group elements in the similar group have similar properties. So he did that. He grouped elements a little bit based upon their weights and their densities, but also properties in certain in these columns here. So Meyer actually did the same thing as well. But again, the reason we remember Mendeleev in his work in developing the periodic table is because Mendeleev understood that, hey, maybe not all of the elements had been discovered at this point, right? We haven't discovered everything on this planet. So he actually left blanks in his periodic table, knowing that, hey, there should be an element that fits right here. It's in this group. It should have this property and this weight. And so he left blanks in his periodic table. And then, within a couple decades or centuries, yes, we ended up finding those elements. He even gave hints, or he had a hypothesis of, oh, you'll probably find this element in, compounds or minerals containing this, because he understood group chemistry. And so that's the reason we remember Mendeleev. So an example of one of the elements that he left blank on his original periodic table is germanium. Right, so germanium is in the same group as carbon and silicon. So at that time, germanium had not been discovered yet, but he left a blank where germanium would be. That's why we remember him. And so the great thing about Mendeleev, what makes him kind of like this genius, so he called his unknown germanium element silicon, meaning that it's underneath silicon. And he even predicted some of its properties, that he knew, oh, it's going to have this type of behavior. It's probably going to have this type of density. And he was pretty close. So here are the predictions of silicon that Mendeleev made, and then what it took, 15 years for them to discover germanium, and he was fairly close. And so that's why we remember him and not Meyer, but we'll give him some credit here too. He was not brilliant enough to leave those blanks in the periodic table. All right, so the properties. The big idea here is that back then in 1890 or 1871, they didn't know what electrons were. They didn't know what protons were yet. So we need to be aware of what things they did know about elements at the time. And at the time, they only really had observations of the elements. So behaviors, you throw the thing in water or it has this density. Those are the types of things they understood about the elements at the time. So how did Mendeleev come up with the groups of these elements? Did he just inspect their electron configuration? Did he just look at their boiling point temperatures? Did he count the number of protons? Or did he use all three of them? What information did Mendeleev use back in the 1800s? Which one? All of them? Did he use all of them? No, yeah, what's the problem with all of them? He didn't know what electrons were. He didn't know what protons were. So what was the only thing that he could use to figure out the ordering of the periodic table? Just B, boiling point temperature. That's all he used, and densities and stuff, because that's all they could measure at the time. I know it's easy for us because we already know the ending of the story, that we already know what protons are, and it's yeah, obviously put them in order of their protons, but he didn't know that. He didn't know that at the time, right? And actually, some of his things were slightly out of order, and they got fixed once they understood what protons were. And so he got the periodic table most of the way there, and so it took, next slide. So let's just talk about the periodic table and how he came up with the idea of calling it the periodic table. His observations were that he saw periodic repeating of certain properties of the elements. So Lithium, sodium, and potassium, those are pretty explodey solids. And so he saw that, looking at these elements, that these elements should be grouped together because they're all kind of explodey. And so he saw this periodic repeating of certain properties, and that's why we call it the periodic table. And so we already learned about this in chapter 2, that columns, these vertical columns, these are called groups, and the horizontal rows are called periods. But now that we know more about electrons, but remember Mendeleev didn't know about electrons back then, we can actually apply what we learned in chapter 6 to these ideas, that these horizontal rows actually represent the principal quantum number n. As we're working on electron configurations, we know that hydrogen is n equals 1, so that starts our 1s subshell. Lithium starts 2, 2s, and 3, 4, etc. So we see these periods, they're not just horizontal rows, they actually represent the n quantum number as well. And then finally, the numbers that we give each group. So we know that lithium is group 1A, beryllium starts group 2A, go over to boron 3, 4, 5, 6, 7, 8A, all of those things. So those group numbers also represent the number of valence electrons for those specific elements. If we write out the full electron configuration, it's those last outermost electrons that make up the valence shell. And so if we count, those number of electrons in that valence shell, we'll see that all group 1A elements, all of them have a very similar electron configuration. All of them are S1, one electron in an S orbital. They're just all in a different shell. So all group 1A elements have one valence electron. All group 6 elements have how many valence electrons? 6, and it's because they all have very similar electron configurations, S2 and then 4 electrons in the p orbital, and that's where we get the 6 valence electrons. So here we're just kind of completing the story of rows and columns that we learned about in chapter 2. A lot of those predictable properties have relevance and has to do with valence electrons and those quantum numbers that we learned about previously. And so we can see how, all group 7A elements have similar properties because they have a similar number of valence electrons. And so that periodic repeating of certain properties makes sense. That's why we call it the periodic table. Okay, so we know now that our periodic table is ordered based upon the number of protons in our nucleus. So the question is, how did we figure out what the atomic number is? Remember, periodic table came first. Our understanding of nuclei and atomic theory came later. So it was the work of Henry Moseley who figured out what the atomic number for all the elements are. And so we know the atomic number is just the number of protons in the nucleus of that atom. And so there's a little bit of review here. So what Henry Moseley did, so we see that he figured out the number of protons or atomic number, a couple decades after the development of the periodic table. So this is what he did. He took all of the elements and studied each one. And what he did is he bombarded a ton of energy at those at an atom. All right, so he basically energized the atom so all of the electrons would get excited. All the electrons in that atom would get excited, and then he observed the emitted light in the form of X-rays that came from those atoms. And so he saw that different elements emitted different energies of X-rays or different energies of light. Does that sound familiar? A little bit in chapter 6. We'll do a little bit of review about that, about how when electrons fall, they do what with light? Light is emitted, but when energy enters an atom, typically those electrons are promoted, they jump. When the atom absorbs energy, when the atom releases energy, when it falls back, that electron falls back down, light is emitted. So what Henry Moseley saw or observed was that emitted light. It was high energy light, it was X-rays. And so he saw every element emitted a different energy or different frequency of light. And so he was able to deduce that the higher energy of light that was emitted indicated that that atom had more protons in its nucleus. All right, so yeah, that's the conclusion. Okay, so conclusion, more protons in the nucleus, higher energy X-rays are emitted. And the reasoning for this is that n equals 1 quantum number, that n equals 1 energy level is lower in energy, so electrons that are on an atom with a lot of protons fall further. The next slide I have explains this. So the idea here, more protons in your nucleus, higher energy X-rays are emitted. So I'll show you why here, right? So why do different elements emit different X-rays in Henry Moseley's experiment? Okay, so let's think about this. Okay, so remember from chapter 6, see this is a little bit of review, so it's not too bad, that the change in energy of our atoms, so you know the distance, the energy gap that the electron jumps or falls, that is equal to the emitted or the photon that's involved with that transition. So remember, electrons, only when they undergo transitions is light involved, either emitted or absorbed. But we're just going to talk about emission right here, right? And the electron has to move. And so when we think about energy of the photon, it's related to that energy gap that electron underwent that transition. So let's pretend we are a stupid electron orbiting a nucleus. All right, so this electron is attracted or repelled by the nucleus? So the nucleus has our protons in it. We are what? We're attracted to the proton or to the nucleus. So let's compare. We're a stupid electron on a hydrogen versus a stupid electron on a helium. In which element is that electron more attracted? Why helium? Why are we more attracted to the helium nucleus? Because yeah, a different charge, right? We're +2. I'm more attracted because an electron is negatively charged. All right, I'm more attracted to a +2 than a +1. Right, great. So if that electron is more attracted to a +2, what happens is that n equals 1 energy level is lower in potential energy. So remember in chemistry, low potential energy, is that good or bad? That's good. Yeah, low negative potential energies is good. It means that we have a stable system. So when we are in an electron on a helium atom, see how I deliberately drew all of these energy levels lower. Right, I drew them lower because they are more attracted to the nucleus because helium's +2 versus our +1 hydrogen atom. Okay, perfect. So here are different energy levels for hydrogen with our 1 proton, for helium with our 2 protons. So, okay. Now let's do Henry Moseley's experiment, where essentially he energizes all of the atoms in that element, and what happens is all of the electrons on that atom get thrown up into the air, all right? But light is only emitted when? When the electrons do what? Fall back down. All right, so if I throw all the electrons in the air, all right, so I got like a bunch of electrons up here, all right? It's only when these electrons fall back down is light emitted. So which electrons fall further? The helium electrons, right? Because see how for hydrogen, this electron's only going to fall, this is the lowest it can fall, but an electron on a helium atom, it can fall much lower to its n equals 1 because that energy level is lower in potential energy. It's more negative. All right, so let's answer these questions. Oh, we kind of already went through them. Which electron is more attracted to the nucleus, hydrogen or helium? Helium. Which electron possesses a more negative, or I'm going to say stable, potential energy, hydrogen or helium? Helium, yes, it's lower because it's more attracted. Attraction means lower potential energy. Okay, so if all of these electrons fall and our final energy level is the first rung, n equals 1, which electron falls the most, hydrogen or helium? Helium, okay. So now let's relate the energy of that fall to the light that Henry Moseley observed. Okay, so a large fall means what about the energy of that photon? Is it a large energy or a small energy? Large energy, yeah, large fall means large energy of that photon. So let's think about energy of the photon. We're relating it to frequency. How does the frequency of that photon change? If we have large energies of photons, that means what? Small frequencies or large frequencies? Let's review our trends. Okay, remember the equations. Energy of our photon equals Planck's constant times frequency. But it also means frequency is the opposite trend of wavelength. We can also rewrite this as hc over wavelength. All right, so you tell me, as energy of our photon increases, how does frequency change? Increases, yes. High energy photons means high frequency. But then how does wavelength change? Decreases, yes. So short wavelengths, high frequencies, high energies. Long wavelengths, small frequencies, small energies. So let's answer this question. As the photon energy increases, frequency of the photon also increases. Or we can also say that wavelength decreases. We can say that too, right? And that's exactly what Henry Moseley saw, right? That as we have more protons in our nucleus, electrons, they're falling further, okay? That their drop is a lot larger, so therefore the frequency or the energy of the emitted photon gets larger as well. And so all of that comes together. Yes? The second one. Yes, okay, so which electron possesses a more negative potential energy? So remember the this equation right there. Electrostatic potential is proportional to Q1 times Q2 over distance. And so what we see is that when Q1, the magnitude of Q1, Q2 changes, because we're making the nucleus +2 instead of +1, we're changing that attraction, the Q1, the magnitude of Q1, Q2 in the numerator. And that's why it becomes more negative. Okay, more attraction means more negative potential energy. So if I go back to this graph, everyone's favorite graph, this one, remember this graph, potential energy, all right? So we see that negative potential energies means more attractions. Does that make sense? Okay, yes, all right, perfect. All right, and this is a concept that'll come up again. We're oftentimes thinking about how attracted is that electron to our nucleus, which is positively charged. All right, so the moral of the story, as number of protons increases in Henry Moseley's experiment, the frequency of the emitted photon increases as well. Sure, you can just memorize that trend, but on an exam, are we gonna just ask you the trend? No, we're gonna ask you to understand, have more understanding of the underlying concept behind here. And this is all the concepts, and it's related to not only potential energy, but our understanding of our quantum numbers and attractions of those electrons as well. Okay, so I got 10 minutes, so I will go over these next two slides that really are the basis of all of the trends and our understanding of energetics of removing and adding electrons to an atom, and that is effective nuclear charge, right? This is a very important concept, right? Because we're constantly going to be battling effective nuclear charge of electrons, comparing it to its N energy level to think about the properties that we see. All right, so, oh yeah, I said that here. So many of the properties we observe, they depend on two things: the electron configuration of your atom, so the number of valence electrons, that's chapter 6, but also how strongly attracted those electrons are to your nucleus. So this is effective nuclear charge. All right, so effective nuclear charge is essentially, if we're thinking about we are an electron, all right, electrons are attracted to a nucleus, which is positively charged. We want to think, okay, how attracted is that electron to the nucleus? And the answer to that, how attracted an electron is to it, depends on where that electron is on that atom. If you are very far away from your nucleus, are you very attracted to the nucleus? Versus if you're really close to the nucleus, you're going to be really attracted to it. So we have to think about that. And so effective nuclear charge allows us to just like kind of calculate how attracted an electron is to a nucleus. So this is the only equation that you are probably going to be given on midterm 3. This one. Actually, so for like 4 chapters, we can put our calculators away. We're not going to pull out our calculators for a long time because this is basically the only equation that we're going to use. effective nuclear charge equals Z minus S. These two numbers are just going to be integers, so hopefully you don't have to pull out your calculator too much. And so the definitions here to calculate this effective nuclear charge is Z is the number of protons in your nucleus, S is shielding, meaning that depending on where your electron is on your atom, some of the other electrons, because they're all negatively charged, are going to shield that positive charge from the nucleus. And I have some examples to talk about it. So for example, and I mentioned it before, here's a sodium nucleus. If we're an electron that's really close to the nucleus, we're going to be really highly attracted to it. That electron's going to have a high effective nuclear charge because it feels a very high positive charge to the nucleus. Versus if we compare it to an electron that's far away from the nucleus, this one's going to feel a weaker attraction to the nucleus because it's further away and there's a bunch of other electrons blocking the full positive charge of that nucleus. So just think about it. Which electron is it going to be easier to rip off this atom? The electron that's really attracted to the nucleus or the one that's just kind of loosely attracted to it? Yeah, so which electron are we going to rip off, the red one or the green one? The red one, because one, it's further away and it's less attracted to the nucleus. And this is the reason why valence electrons are the only electrons involved in chemical reactions. Okay, so the problem is, so Z we can figure out for an atom. S, the screening constant, we figure this out by writing out the electron configuration. All right, so the screening constant is all of the core electrons on that atom. So the next slide I'll explain what this means. Actually, no, let me use an analogy. All right, okay, so remember, all right, effective nuclear charge is how much positive attraction that electron feels to the nucleus. So someone give me a charge, a positive number. How many protons do I have? Give me a number. How many? 24. Okay, so I have 24 protons. So someone sitting in the front, right here, okay, what charge, if you're an electron, all of you are electrons, okay, if I have 24 protons, what positive charge do you feel right now looking at me? 24, yeah, positive 24. Okay, all right, perfect. All right, what about you? All right, you're an electron. I have a positive 24 charge, but there's an electron sitting right in front of you. So what charge do you feel? Do you feel the full 24 plus 24? No, so what's the charge that you feel?
24 minus whatever.
Yeah, so 24 minus all of the electrons in front of you. How many electrons are in front of you? One, so you only feel 23 plus 23. So she is shielding you, all right? That's the S constant. So we're subtracting one. Okay, one, okay, you, right there. Yep, you. What? Yeah, so you're going to subtract how many electrons? 2, because there are 2 electrons sitting in front of you. Even though I'm positive 24, since there's 2 electrons in front of you, you're only going to feel positive 22. All right, perfect. Ooh, that's a perfect segue to this picture, all right? Because who is this? This is Taylor Swift, all right? And so, right, because of her album? Yeah, okay. So the same idea you can think of, because this looks more like an atom. All right, so let's pretend Taylor Swift, what's her charge? Let's say it's 83, all right? She's a positive 83, right? She has 83 protons. And let's say all of these people around her are electrons. So if I was this person right here, that guy, all right, he's an electron. When he looks into the nucleus, what's the charge he sees? 83, positive 83, all right? Because there's no other electron shielding him. But if we go one person back, this person, and they look in, there's a person shielding them. There's one electron shielding them. So what effective nuclear charge does that pink person see? 82, because that one person is shielding them. And then we see it propagate, that the further you go out like this person and they look in, there's a bunch of electrons shielding them, lowering the effective nuclear charge. All right. Okay, so that's how we calculate effective nuclear charge. First, we need to know how many protons we're working with, and then we need to figure out the shielding. All right, but it's not as easy as just counting people in front of you. No, we actually want to count the number of electrons between the nucleus and the electron in question. All right, but usually we are talking about valence electrons, so we're always talking about the people in the back rows. All right, that's what we're calculating here. All right, so let's do an example. This is the slide I want to end on, so that's perfect. So let's do an example. Let's go back to sodium. All right, and the hardest part is trying to figure out what the shielding coefficient is. All right, so let's go back to sodium. So sodium has how many protons? What is Z for sodium? How many protons? 11, yes, it's just the atomic number. All right, so sodium, let's not do blue, let's do pink so you can see it. All right, so sodium has a plus 11 charge in its nucleus. So I'm walking us through how many, or what's the effective nuclear charge of a valence electron on sodium, right? Sodium has a bunch of electrons. The electrons close to the nucleus are going to be highly attracted, high effective nuclear charge, but the electrons on the outside are going to have a lower effective nuclear charge, and that's what we're going to calculate right now. All right, so we got, so what are we trying to do? Z effective equals Z minus S. So we have Z. Now we need to figure out what is the shielding constant for a valence electron on sodium. So the easiest way to do this is to write out the electron configuration of sodium. All right, so here is the electron configuration of sodium, the full one. All right, those are all of the electrons. Which electrons are closest to the nucleus? The 1s, the 2s, or the 3s electrons? 1s. Okay, so these electrons are closest to the nucleus, so they're closest to that positive 11 charge. But right now we are focusing on the valence electrons, so we are sitting over here. All right, we're sitting on the outside, far away from the center stage. Okay, so now we just need to count how many electrons are between that 3s electron and those inner electrons. So you tell me, how many people are sitting in front of you? 10, yep, 10. So our shielding for our valence electron on sodium is 10. So what is our Z effective for that valence electron? It is 1. So what this means is that 3s electron only feels a positive 1 attraction to the nucleus. That's what that means, okay? So we can calculate the effective nuclear charge on any electron, actually, on this nucleus. So let's calculate what is the effective nuclear charge for this time not a valence electron, but an N equals 2 electron. We do the same exact thing, we're just sitting in fancier seats now, in a seat closer to the stage. So it's the same exact strategy. My nucleus is positive 11, so my Z is still plus 11, but now my shielding is different, right? The difference is sitting in the back row versus sitting in a middle row. So since now I'm an N equals 2 electron, I'm one of these electrons in this row, all right? I could be in a S orbital or a P orbital. I don't know which one. I just said N equals 2. So if I look into the center stage, how many electrons are standing between me and the center stage? Just 2 electrons, yeah, so it's just the N equals 1 electrons that I'm focusing on. So my shielding here is 2. So what's the effective nuclear charge on those N equals 2 electrons? Plus 9, all right? And so, okay, so putting it all together, which electron is more attracted to the nucleus? A valence electron, which is N equals 3, or an N equals 2 electron? It would be, yeah, the N equals 2 electron is more attracted to the nucleus. So therefore, those electrons are going to they're going to be closer to the nucleus, all right? And so the question is, you know, for this last example, when I said N equals 2, the idea is, you know, why don't we include like the S and the P electrons here and the N equals 2 in our shielding calculation? So I'm going to go back to my like concert analogy. If you're at a concert and you know, you're sitting in the back row, if you're sitting way in the back row, who's affecting your concert-going experience the most? The people in front of you or the people next to you? the people in front of you. So this is why we don't consider the electrons that are in the same energy level in our shielding calculation. We only care about the electrons in front of us. And so this is what we call the simple shell model. There's actually more complex ways we can calculate effective nuclear charge, but this is the easiest way, and it's actually pretty close to what it is if we would consider the electrons next to us, but it gets us pretty close. All right, so we'll end right there. All right, and so effective nuclear charge, this concept's going to be really important in the rest of this chapter. We'll come back to this on Thursday, so let's do midterm review. And I'll say that my Taylor Swift analogy, I made that up. I made that up. Yeah.